Learn Efficient Pharmacology, Pharmacokinetics Part 3, Estimating Bioavailability. Bioavailability is a fraction, the fraction of the administered drug that reaches the systemic circulation. It is easy to measure the quantity of the drug we administer. But how do we measure the quantity of the drug that reaches the systemic circulation? Obviously, we cannot weigh it like we weighed the administered dose. But there is one value that we can accurately measure: the plasma concentration of the drug. But if we measure the plasma concentrations, we get different values at different points in time. For example, let's consider an orally administered drug. As a drug is being absorbed from the gastrointestinal tract, the plasma concentration tends to rise initially. Later on, as elimination predominates, the plasma concentration tends to fall. So the plasma concentration time curve will look like this. Now, if we administer the drug intravenously, absorption is bypassed. All of the drug reaches the systemic circulation instantaneously. So the plasma concentration is at its peak initially, and the plasma concentration time curve looks like this. But how can we use these plasma concentration time curves to estimate bioavailability? We have learned in math that in a time curve, the area under the curve, or AUC, represents the cumulative change over a time interval. For example, assume that the daily revenue of an e-commerce platform, say Amazon, is plotted against time for a week. Then the area under this curve will represent how much the total revenue of Amazon was for this week. We can apply the same principle to the plasma concentration time curve. Here, the area under the curve represents how much the body's total exposure to the drug was. That is the systemic exposure to the drug from its administration to complete elimination. Now, if the fraction of the drug reaching the systemic circulation is greater, AUC would be larger. That is, AUC is proportional to the fraction that reaches the systemic circulation. This fraction we know is bioavailability F. So, AUC oral is proportional to F oral, AUC IV is proportional to F IV. Dividing the two, AUC oral divided by AUC IV is equal to F oral divided by F IV. We know that if a drug is administered intravenously, 100% of it reaches the systemic circulation. That is, F IV is equal to 100% or 1. So the equation becomes AUC oral divided by AUC IV is equal to F oral. That is, oral bioavailability is equal to AUC oral divided by AUC IV. Similarly, bioavailability for other routes such as intramuscular, transdermal, etc. can also be estimated. Since the comparison here is with the intravenous route, where bioavailability is 100% or absolute, this is termed absolute bioavailability. For example, the term absolute oral bioavailability is used when AUC oral is compared with AUC IV. Sometimes bioavailability of one non-intravenous formulation is estimated relative to another non-intravenous formulation. For example, oral versus sublingual tablets. This gives us relative bioavailability. Up to this point, we have been focusing on AUC, which represents how much of the drug the body was exposed to. This is the extent of bioavailability. Consider another formulation of this drug containing the same dose, which gives us this plot. Here, the AUCs are similar, but the second formulation is absorbed very slowly, and the drug does not achieve a plasma concentration high enough for a therapeutic effect. Thus, how fast the drug reaches the circulation or the rate of bioavailability is also important. We can actually see this on the plasma concentration time curve. The maximum plasma concentration that is achieved is Cmax. The time taken to achieve Cmax is Tmax. So Tmax shows how quickly the drug reaches the systemic circulation. Thus, it is a measure of the rate of bioavailability. So, while AUC represents the extent of bioavailability, Cmax and Tmax represents its rate. When two formulations of a drug have comparable rate and extent of bioavailability, we call those formulations bioequivalent. You may recall that we started out measuring plasma concentrations. However, it was only when we plotted these values over time that we were able to quantify absorption in a meaningful way. No wonder why pharmacokinetics is also defined as the study of the time course of a drug in the body. In the upcoming videos of the series, we will see how this time course applies for distribution and elimination. Here are some good to know facts. This is a summary of our discussion.